name is Bill Wabbersen. I'm a nuclear engineer. I work at Savannah RPSEC. Today, what's the center of the atom? Nucleus. We're going to take a journey to the center of the atom. And that's nuclear engineers. That's what we deal with every day. So this is the first class ever taught this lesson. So let's hope it goes well. But it'll be exciting to do it together. So it's a lot of, we're going to hopefully have fun, but you guys let me know what you think of it. We said this is the symbol of the atom, right? The nucleus is in the middle, so we're going to journey to the center of the atom. And wipe away the electrons and just focus on the center. What's in the center of the atom? The nucleus has two parts.
Protons and neutrons.
So I'm representing the Citizens for Nuclear Technology Awareness and the American Nuclear Society. I'm the past president of the American Nuclear Society, and I'm on speaker bureau for CNTA. And so they're right here in Aiken, both of them. So if you ever want to learn anything about nuclear, we have a website you can look us up. Now, this is the nucleus. I drew this picture. For those you can't see, I'll slide over here. I drew this picture, and what you'll see is the purple and black are the protons and neutrons. You can see the color. And the electrons fly around the outside in the electron cloud. Each proton and neutron have a mass of about 1. This is called atomic mass unit, so about the same size, neutron and proton. The neutron's actually just a little bit bigger. Electrons are really tiny. I drew them the same size here so you can see them, but they're very, very tiny, 1/1800th. If I drew them the relative size, you wouldn't even see them. They're so tiny. So electrons are what chemistry people deal with. Nuclear engineers only deal with the nucleus. What is this called?
Periodic table.
Very good. I'm very impressed. Periodic table. Now it's got a funny shape, doesn't it?
Yes.
It's got a weird shape to it, I think. This is for chemistry people. It's designed all based on the electrons. And nuclear people, we deal with the nucleus. So we really don't use this chart very much. So that's why it has a very unusual shape. In reality, this box down here fits right in where those two boxes are. So it's really wide, a lot wider than this, but it's easier to print on a page when they do it this way. So what we're going to do is today we're going to build a periodic table, and that's what chemistry people use, because this is built based on electrons. And then we're going to convert it to what nuclear people use. And the way we're going to do that is based on what are called isotopes. Does anybody know what an isotope is? Yes.
It's a form with different size nucleuses with like more protons and neutrons.
It has the same number of protons. You can see this red is a proton, and a different number of neutrons. So it has a different weight, but it has the same number of protons and electrons. See that? So you had it. So these are 3 isotopes of hydrogen. So hydrogen 1, hydrogen 2, and hydrogen 3. This is called tritium. The neutrons act like glue. If you had 2 protons that you were going to push together, they're both of a charge of 1 plus 1. Would they go together or would they repel? Would they attract or repel? They would repel. Like things repel, right? So the neutrons act like a glue. Since they don't have a charge, you can stick it to a proton. Then you can stick another proton to it. So it acts like glue. But if you don't have enough glue or you have too much glue, things break apart. And that's where radioactivity is. That's when you become radioactive. And it breaks apart. Does that make sense? So we're going to do some of that. We have to do one thing first. We have to understand when we do our exercise, you need to understand the numbers. There's going to be a letter here, and a number here, and a number here. You guys know this already? What is this? What is this number? Right here, you see carbon, 6, and 12. So what's the 6?
The atomic number.
It's atomic number. Very good. What is that?
It's like it's like how many neutrons are in the
How many protons? How many protons? It's also how many electrons. What you're going to have to do is you're going to have to do this yourself in a minute. So you got to pay attention to this part really closely. So this is the number of protons, and what is this number up here?
The number of atomic mass.
Atomic mass.
Atomic mass, and it is the number of protons plus the number of neutrons. So if you want to know how many neutrons, how do you do it? What do you do?
You subtract the atomic
Subtract
number
one from the other.
atomic
That's
mass.
exactly right. All right, we're in practice, okay? 1 hydrogen 1. How many protons are there? 1? Do you agree? 1. 3 lithium 7. How many neutrons are there? 4. 8 oxygen 17. Protons are 9?
8.
Protons are 8. That is correct. And 1 hydrogen 1. How many neutrons are there? 0. You guys can do math well. All right. Great. Let's go build our periodic table. Y'all come over here. This is what the periodic table looks like when you add the lanthanides and the actinides, that one strip back in the middle. And there are some that are missing. They start up in the corner with hydrogen and ends in Copernican down here at the bottom. And the number I have on the bottom is the number of isotopes each one has. So what I do is I have a bunch of tiles here. I want you guys to fill in the missing spots. As a group, do that. Put them on top of, put it right there. You click, Mercury is right in front of you.
No, Mercury goes.
Right in front of you, just up one, right, one over, Mercury, right on top of it. Up.
Oh, I thought.
And then uranium, it's not a blank, now put a uranium, it's over to your left, all the way over there. And Copernican's right below Mercury. Okay, now, and that's kind of straightforward, simple, but if you were to think of these, this is the number of, this is the average. You can see the numbers 1.01 for hydrogen. What's it for lithium, the atomic mass number?
6.94.
6.94. It's not a real whole number. That's an average of all the isotopes that there are that exist. These right here are all of the isotopes. What I'd like you to do as a group, I want you to take that whole box of tiles. What I want you to do is I want you to stack them under their element. And I want them in numerical order with the low number on the top and the high number on the bottom. They don't go there. They don't go here. What they do is you need to stack them up on the periodic table over there.
But if you guys have ones that go on this side, just send them over. We'll send over piles of the
So
ones.
we gotta find.
Here's
phosphorus.
How close are you done? Let's go ahead and finish. You notice there's pretty high stacks, right? Pretty high stacks. The other thing is you can notice is that they're different colors. So let's spread out so everybody can see, and I'll describe this. What I can tell you is the green tiles are the stable isotopes. They're not radioactive. The blue tiles are radioactive isotopes, and the red ones are so unstable they don't even last a second. But these are all the isotopes that have been discovered for just these. If we did it for all of them, we'd be here for a whole day. And so to do all of this. And this, from a nuclear engineer standpoint, is very hard to see what's all these different isotopes. So we use a different chart because you can see this how it's 3D. But I'm going to show you one other thing. The most isotopes there are on, this is mercury. And these are stacked in order with the lowest number on top and the highest number on the bottom. And this is uranium. It goes that way. And this is Copernican. It goes that way. It actually goes that way. So you can see that there's stable isotopes in the middle, and then as you get too much or too little neutrons, it becomes radioactive, and if you get more, it becomes unstable. So you can see that. If we had the time to put them in order, you'd see it on every stack, that same symmetry. So what we're going to do now is we're going to make a chart of the nuclides. This is what every nuclear engineer uses, this chart over here. And this should be just one layer for all these tiles. The protons go up the left side, the y-axis, and the number of neutrons are the x-axis. You see that? So I'm going to put the first two tiles on there. This is a neutron. A neutron is a 0N1. It has 0 protons and 1 neutron. So it goes right there. 1 neutron, 0 protons. Hydrogen is the opposite. It has 1 proton and no neutrons. So you're going to take all of those tiles over there that are, the white ones leave over there, but every rest of them I want you to lay them out on this chart. And you can see they'll be in order to them. All the heliums will go this way, the berylliums will go this way.
Actually, put the chlorine on the other side, the chlorine on the top, and then they're going to go in a row down here.
This one's easy.
I'm telling you. You're starting to see there are some patterns here, how they run the numbers run in both directions.
What are you guys doing?
Yeah, a lot of
Your fluorines are way off. Your 16 and 17 move into this gap over here. There you go. And then the rest of them all slide down. There you go. Blue is, and the red is unstable. Now what happens is the green forms a line. You see that? all in a diagonal, that's called the line of stability. Make sense? And so what happens, all nuclear technologies utilize the line of stability. Every one of them. Medicine, nuclear power, we use it as how to fill the cereal boxes in your cereal. It's all nuclear technology utilize it. What we do is we push an atom off of the line of stability, and as it comes back on, it gives off radiation. We can push it in either direction. There's a nuclear medicine machine over at MCG, I guess it has a new name now, the medical, Georgia Medical Sciences or something like that. It's called a positron emission tomography. And that is, positrons are on this side of the line of stability. And so we push them off this way. Fluorine-18 is one of those that we use. So what happens is, all nuclear technology, by understanding this phenomena, we push an element off of the line of stability, and when it comes back, we utilize the radiation that it gives off. This, if you remember, we've used very little of the periodic table. The chart is much larger. The chart is actually this big. I'm going to show you what it looks like. This is what nuclear engineers have on their walls instead of the periodic table. And they're very tiny, and it's a giant, one big slash, and we divide it into thirds. You see how it's 3 pieces? So it all fits on one chart. And so all of the data we use is in here. And see, it's really small writing, isn't it? So most nuclear engineers only have this on the wall as kind of a brag sheet. What we really use is we convert it to a book to where we can read it on smaller levels. And so it's broken into hundreds of pieces. And so we actually use this every day to understand nuclear technology. You guys just built your own chart of nuclides. The next thing we're going to do is each table, if you remember what table you're at, I want you to pick one isotope, either green or red, and try to stay away from the bigger ones because they're a little more. There's an interactive nucleus down in the lobby, and we're going to go build our own nucleus down there. So each team, who is from table 1, raise your hand. Now decide on an isotope, make it green or red, and pick it up. And we're going to go downstairs and build it. Now, who's team 1? Raise your hand. Step to the front, team 1.
Let's build a nucleus.
Now the red ones are protons. The blue ones are neutrons.
Place the protons and neutrons on the table.
So you have to figure out how many you need of each from your isotope. Calculate your head, and then pick up the number of protons and neutrons, set them in the holes, and then push the go button. The red ones are protons. The blue ones are neutrons. Put them in the table. So everyone, you probably go ahead and calculate yours while you're waiting. Don't hit it. You gotta have your red ones. Don't hit the button, guys. As soon as you hit the button, it's going to drop out, so you have to start over. All right, count. How many?
We'll tell you what you got.
Tell me when you're ready. So 10 and 9? Okay, when you push the button, it'll tell you what you made. And it'll tell you its usage. I hit the button, it'll tell you more about it. Are you ready? Let's try this one.
Wow, you have made neon 18. This form of neon is radioactive and emits a positive. There are currently no known uses for neon 18. Can you think of
It
them?
lasts about 2 seconds, so go ahead.
Many radioactive materials are used in medicine.
What Where can you find double-sided tape?
Be better. The stickiness is lacking.
This class is not focus on elements, but focus on isotopes, because that's what is determined by the nucleus. The nucleus is protons and neutrons. So you went from a periodic table, which you learned, should have learned in chemistry, and then moved on to the chart of nuclides, which this is what the whole thing looks like here. And then after that, you saw the uses of nuclear technologies. There's uses in agriculture and medicine and industry. It is helping in your house with smoke detectors. Exit signs are made with radioactive materials. So they're all done using nuclear technologies and determining that line of stability. So any questions? I think this is everything. So what do you think? You're the very first class that ever did it. There are some things we can work on so that everybody can get around the table so that it's not so crowded. But was it fun?
Yeah.
So that's what it was meant to be fun. So thank you, everybody. And if you have any questions, just ask me after class.
What kind of little hint